All right, so in our chapter on lipids, there's some time we could spend talking about saturated versus unsaturated fats and oils. I think we did a lot of that in 351. And so I don't want to spend hardly any time on that now. I do want you to be aware of the impact of a double bond, a cis double bond in a fatty acid or fat or oil on its melting temperature, why fats are solid and oils are liquids. I do want you to have an idea of why unsaturated fats are subject to like rancidity in an oxygen environment because of radical allylic oxidation of a double bond. I also want you to have some experience with the structure of, say, phospholipids and what the different head groups are. I'd like you to know why a phospholipid forms a bilayer versus a fatty acid forms a micelle. But a lot of that is stuff you can get from the chapter without my help. And so I'd rather spend time on a class of lipids that are called terpenes, in part just because it's sort of fun. So I'm not going to ask you, for example, to draw the structure of a prostaglandin from memory. I don't find that particularly useful. I'm also really not going to have you focus on what the biological activity of prostaglandins or leukotrienes or eicosanoids are. I think all of that you can get in the future on your own without a lot of help. But I think terpene chemistry is an opportunity to put together a lot of what you've seen before in complicated and fun kind of ways, and so that's, I think, what I'd like to spend a lot of our time on. So again, follow the study guide, do what it says for you to do, but the time we're going to spend in class is mostly going to be on terpenes. All right, so what is a terpene? Terpenes are molecules that are composed of isoprene units. What is an isoprene unit? Well, isoprene itself is the name of a molecule that looks like this. That's isoprene. And an isoprene unit has this basic connectivity of 5 carbons. It doesn't make a huge amount of sense why I've chosen to do this, but I tend to number them like this: 1, 2, 3, 4, and 5. I realize that's not IUPAC, but the thing that defines an isoprene unit within a natural product is this 5-unit chunk of carbons with a branching methyl group on carbon 3. And being able to recognize that isoprene unit in an existing natural product is the first step in being able to propose a reasonable synthesis or a reasonable mechanism for how that natural product forms. Let me give you a couple examples. An essential oil from citrus is called limonene. And I think if you were with me for 351, you've probably seen a terpene before. We've probably seen some mechanism and or, basically mechanism questions related to terpenes. This is the structure of limonene. I'm not showing stereochemistry because it doesn't matter for our discussion. How do you identify the isoprene units in limonene? Well, first, one of the reasons you can tell that it's a terpene is because it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, or 2 isoprene units. Molecules that are composed of two isoprene units, interestingly enough, are called monoterpenes. So a terpene is two isoprene units, 10 carbons. If you want to identify the isoprene units in limonene, you start by looking for branching methyl groups. Anytime you have a branching methyl group, that could have been carbon 3 of an isoprene unit, right? So that I see a methyl group here, a carbon that has a branching methyl group there, and another here. And then you sort of start filling in the rest of the numbers as best you can, right? Bonded to carbon 3. Yeah, thank you, Noah, sorry. The carbon that has the branching methyl group, the methyl group is 3. The carbon that has the branching methyl group is 2. All right, so then you start to fill in the other numbers. 1, 2, 3. And sometimes there will be multiple ways you can do this, and that's okay. Notice how here is one isoprene subunit, and here is another isoprene subunit. And you can start to pay attention to how they're connected to each other. Carbon 5 of one subunit is connected to carbon 1 of the other, and then there's another linkage here between isoprene subunits. So it's important to be able to identify the isoprene subunits and then see what the bonds are between those subunits. Notice what we're not doing. We're not worrying about where the double bonds are at all. We're just looking at the single bond connectivity. Yeah.
So if this one you just drew here had no double bonds, or if it had more double bonds than it has now, would it still be the monoterpene? Or would it?
Yes, if it had 0 double bonds or more double bonds than it has now, would it still be a monoterpene? Yes. Are the 1 and 3 on the bottom interchangeable? Yeah, in the sense that we're ignoring the double bonds. So branching carbon instead of branching methyl group is probably fine. I suppose, yeah, you could just as easily have numbered this 1, 2, 3, and that would have been fine. So identifying isoprene units, we are paying attention to branching methyls, but we are ignoring double bonds. We're also going to ignore oxygens or other heteroatoms. For example, a related molecule to limonene is menthol, which is in peppermint oil. I'm not showing you stereochemistry. Same basic connectivity of isoprene units though, right? Even though we're ignoring the OH group. Okay, so look for the branching methyl groups. We'll call the methyl group 3, and the carbon that's bonded to that methyl group we'll call 2, and then we'll number everything else accordingly. There, we will encounter situations where we could have chosen to number it differently, and often that's almost always okay, as long as you get the branching methyl groups right. What do I mean by this? Well, I could have taken this same structure of menthol, and what if I had chosen to number things 1, 2, 3, 4, 5? Well, and the real question is, if I do that, is the branching methyl group on the other isoprene unit still in the right place? What I'm telling you is I don't have a good way to tell you which one of these is better. Either of them is okay. All right? But both of them are going to give me a clue as to what bonds I needed to have made in the process of making this molecule. Let's do a couple of others. Oops. Sorry, there we go. This is geraniol. It's from rose oil. Identifying the isoprene units here, again, 2 is where the branching methyl groups are. We'll call the branching methyl groups 3. And then everything you fill in there relative to the branching methyl group, 1, 2, 3, 4, oh, can't count. 1, 2, 3, 4, 5. Here is a bond between isoprene subunits. This is the first subunit, this is the second subunit. All right. And there are others we could do. Let's see. Should we? Why not? This one's horrible. This is called alpha-pinene. If you don't like that, we could draw it this way, but I doubt you'll like this any better. Oops. It's tough to draw. Okay. That's something straight out of your nightmares because it's a bicyclic system. 6-membered rings you're okay with, but what the heck is going on here in the middle? Start by identifying the branching methyl groups and the carbons that are attached to them. Oops. Then see if you can figure things out from there. Here it makes sense for the carbon adjacent to carbon 2 there to be 1. 1, 2, 3. Then I could go 4 and 5 here, and that would be 1 isoprene unit. And then 1, 2, 3, 4, 5. So 10 carbons, there's my 2 isoprene units. Do you see that basic sigma bond connectivity? You get the branching methyl group, go ahead.
Could you, instead of doing the blue one that way, could you, instead of the 5 being right there, could it be a 1, and then the 4 be the 2, and then...
Yep. Yeah, you totally could have done that. And in fact, probably when there are, especially when we make molecules that are chiral, probably that other arrangement, we're just talking about it, identifying the units, but my mind is jumping ahead to the biosynthesis, and probably if you number it a different way, probably that leads to a different enantiomer, but no. So I'm getting ahead of myself. You're asking, could I have done 1, 2, 3, and then done this 4 and 5? The problem with that, is that the question?
It was similar, but...
Which one did you want to?
So I was saying...
Oh, go the other way. Okay. Right, the problem with what I was doing then is where's pink carbon 1 gonna be? But no, you were saying let's do 4, 5, and then can I do 1, 2, 3, 4, and 5 like this? Yep. That's reasonable too. Okay. Why are we worrying about all of this? Well, all of these natural products come from one precursor. All of them are come from the following precursor, which is called geranyl pyrophosphate. Yeah. All right, so this portion here is called the pyrophosphate group. It is often bound by magnesium ions, by a magnesium ion, which helps sort of attenuate the charge and helps this be a better leaving group. We're just going to color this in as green. We could look at the pKa of the corresponding conjugate acid of pyrophosphate, and it would definitely be a strong acid. So this is just a good leaving group. And notice that the good leaving group is at an allylic position, so that if it left, it would be a resonance stabilized carbocation. Now, you may have looked at that and said, oh, that's a primary carbon that leaving group's bonded to, so this thing isn't going to do any SN1 type chemistry. And the answer is no, it will do SN1 type chemistry because it is at the allylic position, and if it left, it would have a resonance stabilized carbocation. I'll draw that for you just so you can see. If the leaving group leaves, see how that's resonance stabilized? Final exam question, which atoms share the positive charge? Okay, so the other thing we can do is to identify the isoprene units within geranyl pyrophosphate. Here's the branching carbons where the methyl group's coming off. Methyl group is carbon 3. Branching carbon is carbon 2, and you can fill in the rest from there. And notice that in this precursor, geranyl pyrophosphate, we've already got a bond between isoprene units. It's the bond between carbon 5 of one subunit and carbon 1 of another. That's already built into this precursor. So as we look back at places, at some of these molecules, anytime we have a bond between 5 and 1, that already came in the precursor. So that narrows the number of things you got to do when drawing the mechanism of forming one of these from another. So I would look at this bond between 5 and 1 in geraniol and say, okay, we got that. That's already there. In fact, to make geraniol from geranyl pyrophosphate, you just need to replace this good leaving group with an OH group. But if I look at, say, limonene, notice in limonene I have one of the two bonds between isoprene units is a bond between 5 and 1. That was already present in what I'm calling the linear precursor. Similarly, the bond between 5 and 1 in menthol was already present in the linear precursor. Another thing about geranyl pyrophosphate and generally linear terpenes is they have a head and a tail. And I'm not sure which one you want to call head versus tail. The two methyl groups at the end of this remind me of a fishtail, so I'm going to call that a tail. And then the leaving group we'll call the head. But there's directionality. What I mean is there's directionality to these linear terpene precursors. There's a tail and there's a head, and the individual subunits are connected in head to tail fashion. Carbon 5 of one isoprene unit is connected to carbon 1 of the next one, head to tail. And we'll show you, I'll start to show you how, I want to show you how geranyl pyrophosphate is synthesized from two simpler precursors. And then we're going to start to connect the dots between something like this and all of these structures that I've shown you so far, and some even more complicated ones. Questions you want to ask? Yeah? Okay. All right. So we get geranyl pyrophosphate from two simpler precursors. The first is this one, and I'm going to abbreviate the pyrophosphate group as shown here. When you see that, think of what I've drawn for you above, just a good leaving group. Okay. You don't need to know the name of this. It's called dimethyl allyl pyrophosphate. Notice that you have a good leaving group at the allylic carbon. So this is spring-loaded for SN2 chemistry and to be the electrophile, because if the leaving group leaves, you end up with this resonance-stabilized carbocation. I meant SN1, even though I said SN2, sorry. Dang it. Okay, the second precursor is a nucleophile in the reaction, but it comes also sort of spring-loaded with this good leaving group. But notice that that good leaving group is not allylic. That position is not adjacent to the double bond. It's adjacent to an allylic carbon. And the key business end of this molecule is the nucleophilic tail. That is, it's got a pi bond, an isolated pi bond, and from 351 you're used to thinking of those as nucleophiles. So dimethyl allyl pyrophosphate has an electrophilic head. The subunit I just drew over here is called isopentenyl pyrophosphate. That's got a nucleophilic tail, and the reaction that's going to happen here is pi bond attacks, pi bond nucleophile attacks carbocation electrophile. You've seen stuff like that again and again and again in 351 and 352. That makes a new carbon-carbon bond. So let's go ahead and color the electrophile blue, and I suppose we could have made a different choice there. Oh well. Color the nucleophile pink. Let's draw the bond that we formed between those two groups. So here's carbons 1, 2, 3, 4, 5 of what was our electrophile. We just made a bond between carbon 5 of the electrophile While we're at it, let's decide based on stuff we know from 351. Carbons 1 and 2 are involved in the pi bond. Who gets the bond with carbon 5 over here? Pink 1 or pink 2? And why? Right, it's all to do with carbocation stability, right? You want your bond to be with pink carbon 1 so that more substituted pink carbon 2 can have the positive charge where that's more stable, right? More substituted carbons, more stable carbocations. Now, so that's leaving group leaves is sort of an SN1 type step. What we did here is sort of pi bond attacks carbocation. What have I got to do to get from this carbocation to my geranyl pyrophosphate? Look at the connectivity. What's the difference? What kind of reaction gets me from here to here? Right, E1 style elimination of a proton, that's beta to a positive charge. Now, look at that. How many protons beta to a positive charge do I have? Got a lot, right? 3 different carbons that are beta to the positive charge. Which one gets removed to give me this product? Right. Now, there are a lot of choices that we're talking about biosynthesis, so this is controlled by the enzyme. But there were other choices. Can you think of a reason strategically why nature would have wanted to put the double bond there between 2 and 4 instead of between 3 and 2 or 1 and 2? What does it get you? Yes, exactly. You position the double bond so suddenly carbon 5 is now allylic and you're set up for future chemistry. Because if we want to, we can put another, we can start from geranyl pyrophosphate and we can repeat the step below using this as our leaving group and this is another nucleophile, and we can string another isoprene unit on the head of that geranyl pyrophosphate. And so that's just incremental iterative synthesis. This is actually how natural latex is made, is through this process. Okay, so you've seen some of the basic steps that can happen in terpene chemistry. Leaving group leaves, sort of substitution type chemistry, pi bond attacks carbocation, and elimination to create a new double bond. One thing you haven't seen really yet is carbocation rearrangement, but we will get there. So, questions so far? All right, let's talk about stereochemistry. In the geranyl pyrophosphate, notice that the double bonds are all E. And sometimes we have to make some adjustments to deal with that fact. So I want to show you how we get limonene from the geranyl pyrophosphate precursor. All right. So to do this, let's actually copy the structure of limonene. And let's also copy the structure of geranyl pyrophosphate, whatever. And let's look at the isoprene units here as we've identified them, and notice that already in limonene, we have the characteristic head to tail bond between 5 of the blue unit and 1 of the pink unit. That's a bond we don't have to make. If we start with geranyl pyrophosphate. By the way, your biochemistry texts and I think your OChem text are going to tire really quickly at writing out geranyl pyrophosphate, so they're going to abbreviate that. Okay, so it looks like I need a bond in this process. I need to make a bond between 4 and 5. The other thing it looks like I'm going to need to do, well, one other important thing is if you notice this double bond between 2 and 4 is no longer E, it's Z. It has to be part of a 6-membered ring. So part of what we're going to need to do is going to be taking into account the fact that that pi bond in the E isoprene unit is, in the pink isoprene unit is Z instead of E. What I'm going to do now is I'm going to redraw geranyl pyrophosphate in a way that maybe better illustrates the connection between GPP and limonene. Okay. Now, notice that in limonene, I need a bond between 4 and 5, right? Notice that carbon 4 is involved in a pi bond in GPP. Notice that carbon 5 is an allylic carbon. I could turn carbon 5 into an electrophile by having the leaving group leave, and then that pi bond could attack. The problem is that carbon's too far away because of the stereochemistry, the E stereochemistry of this double bond. So nature takes care of that in the following way, and you're going to look at it and you're going to think, well, this is dumb. What's going on? Why does it have to be this way? But there's good evidence that it is. Leaving group leaves to give you resonance stabilized carbocation. So that's sort of an SN1 type step. Leaving group leaves to give you a resonance stabilized carbocation. I'm going to draw the other resonance structure. Now you may be looking at that at this stage and say, great, now we've got a single bond between pink carbon 2 and pink carbon 4, so that we can simply rotate around that bond and bring carbon 5 now down closer, pink carbon 5, down now closer to blue carbon 4. And that's a reasonable thing to think, but you would be wrong. And the reason for that is if I rotate around the bond between carbons 2 and 4, I'm breaking conjugation. That resonance only works when all of the carbons 2, 3, 2, 4, and 5 are in the same plane with their p orbitals all lined up. So it turns out to facilitate rotation around carbon 2, a bond between carbon 2 and 4, nature temporarily has the pyrophosphate leaving group hop back on. At that stage then, it's easy for us to rotate around that carbon-carbon bond. This isn't even an isomerization, it's just a conformational change. I can rotate around that carbon-carbon bond. When I do then the pyrophosphate leaving group leaves. And now everything's set for my next step. And I could draw the carbocation like that. Again, I realize that many of you are going to want to get to this point and just say, oh yeah, rotate around that carbon-carbon bond and you're good. And I suppose that's fine. But what nature actually does is it causes the leaving group to hop back onto the tertiary carbon, breaking the need for resonance stabilization and allowing this bond between 2 and 4 to rotate freely. And then once I've got it rotated in the right orientation, then the leaving group leaves for real, for good this time, giving me my resonance stabilized carbocation that is in exactly the right position now to react. Okay, questions you want to ask about that? All right, so I realize this is tedious with all the numbers here, but keeping track of the carbons is actually the key to not getting lost. Now, carbon 4 is close to carbon 5. Pi electrons attack carbocation. We get a new bond between 4 and 5. The reason we do that is so that the positive charge can be on carbon 2, the more substituted carbon, where it's more stable. Here is the new bond we made between 4 and 5. Oops. Now, compare where we are now to where we need to be with limonene. How do I get from here to the limonene product? Go ahead.
So is the only reason that double bond doesn't attack carbocation is because it's too far?
That's right. Why doesn't the double bond attack on the tertiary carbon? First, remember that these are not two separate carbocations. That positive charge is delocalized on both carbons. So it's not like one's more stable than the other. They're both the same structure. It's just you've got positive charge in both places. And yeah, if you attacked there, that would be a 1, 2, 3, 4 membered ring. So it makes sense for the 6-membered ring to happen preferentially. Okay, what else? How do I get from here to the limonene product? What's missing? The pi bond between 1 and 2, which I can get through a simple E1 elimination type step, right? And suddenly I've made the smell of citrus. Okay. Now, this is a stereocenter. Carbon 4 of the blue isoprene subunit is a stereocenter. And its stereochemistry is controlled by this step, whether or not the pi bond attacks the carbocation from above or below, or which face of the alkene gets the carbocation. That's controlled by the enzyme, and so we're not going to worry about where that stereochemistry comes from. All right, so that's limonene. Now, it turns out that the connection between limonene and there's a connection between limonene and then this horrible alpha-pinene product that we need to think about. So let's look at limonene again. And let's look at alpha-pinene and the bonds that we, let's see if we can identify in alpha-pinene the bonds that we would have had to make. All right, as we've identified these isoprene subunits, you've got a bond between 1 and 5. That's from the linear GPP precursor, so we don't have to do that. That one's already done for us. Notice in alpha-pinene we have a bond between 4 and 5. Oh, but look, that bond between 4 and 5 we made previously 4 of blue and 5 of pink. We made that previously in the limonene process, right? By the time we got to this carbocation, we had already made a bond between 4 and 5. So my real question is, if we look at this carbocation, instead of doing an E1 elimination type step, is there something else we might have done? The other bond that's not present in this carbocation is the bond between pink carbon 1 or it's this bond here, I guess, between carbon 2 of the blue and excuse me, carbon 1 of the pink. All right. So take a look at this intermediate and see if you can figure out how I could have gotten a bond between 1 and 2. Let me maybe give you a hint. Carbon 1 is an allylic carbon. It's adjacent to a pi bond. So it's probably okay to isomerize to that. And in fact, if we're ignoring stereochemistry, we've just sort of flipped it over, right? And it's not, yeah, sorry. So, to some extent, what I just did is we could have chosen our isoprene units a little bit differently, but it's, if I removed a proton from 1, then I would have a resonance stabilized carbanion, and I could reprotonate on carbon 4, and that could remove the double bond and put it between pink 1, 2, 3, 4, and 5. And then, okay. So, how about now? Can you see a reaction whereby I could get a bond between pink 1 and blue 2? What is that? What kind of reaction is that? That's pi bond attacks carbocation, right? Now, this is an intramolecular process, which I know you hate. And it basically involves the pi bond reaching down and attacking the positive charge to create a new bond. Now, does it make sense which of the two bonds, pink 1 or 2, should get the new bond? Pink 1, right? Because that would leave the positive charge on pink 2 where it's more stabilized by resonance. So let's, when doing this, I found it's somewhat helpful. Oh shoot, we're out of time. Well, I don't care what's helpful. You guys figure it out. See if you can draw the product that you would get from that, and then see if you can connect it ultimately to this alpha pinene product. We'll pick up with that next time. All right, here we go. Coming down to the end of it, not that many weeks or lectures left. You have an exam that begins Thursday. I think we probably will just get through Chapter 25 lipids and not through Chapter 26 nucleic acids. So if you're planning for the future, we probably won't get to nucleic acids, at least before the next exam. All right, carbohydrates. We drew the structure of beta-D-glucopyranose, and we talked about where what each portion of the name, how that's reflected in the structural features. So one thing I wanted to add is that it's easiest to memorize carbohydrates when you know what beta-D-glucopyranose looks like. We talked about the alpha anomer, which is where the OH group on the hemiacetal carbon is pointing down instead of up. Notice that in beta-D-glucopyranose, all the groups are equatorial, so that's easy. There are a few other common sugars that you ought to be aware of. This, as I said, down, up, down pattern of C2, C3, and C4 is glucose. In contrast, if it's up, up, down, that's what we call mannose. So beta-D mannopyranose would be if we had everything the same, only on C2 the OH group is up. So mannose is called the C2 epimer of glucose, or the C2 diastereomer of glucose. You just got to memorize glucose and then know that you flip the OH group on carbon 2, and that's mannose. Mannose is a pretty common carbohydrate. It's found in the large branch carbohydrates that are present in glycoproteins. And then another one that you have heard of likely is galactose. So the galacto is the beta-D galactopyranose is the C4 epimer of glucose. And these are the ones that glucose, mannose, and galactose are the major carbohydrates that show up commonly in biology in classes, especially that you'll see in the future in biochemistry or something. So C1, 2, 3, 4, that's galactose. So glucose, the pattern was down, up, down. Mannose, it's up, up, down, and then galactose, it's down, up, and up. All right. There's a lot more carbohydrates than that, but those are ones that I want you to know. Yes?
Would you prefer to memorize the Hawthorne projections or the chair?
Right. So there are multiple ways of representing sugars. You mentioned Hawthorne projection. And basically, the Hawthorne projection is something like a hybrid between the chair view and the simply overhead view of glucose. So if you want to view glucose from overhead, beta D glucopyranose, you just got to use dashes and wedges in the appropriate locations. Let's see, and I apparently can't do that. Down, up, down, and then the hydroxymethyl group. So that's fine, and a lot of people will draw it this way. In biochemistry textbooks, it's common to sort of tilt this on its side and not draw a chair, but draw a six-membered ring in a way that just keeps track of stereochemistry. So I'm drawing for you what is called the Hawthorne or Haworth. I'm not sure actually what it is. Haworth, Hawthorne. Should we look it up? I don't care. Whatever the name of the projection is, it's scarcely worth a name because you draw a ring, the six-membered ring, in a way that only gives you the shape and not only gives you the idea that it's a six-membered ring and not its actual shape. And then for groups that are pointing upward, you draw a line straight upward. For groups that are pointing downward, you draw a line straight downward. That does not look like a tetrahedral sp3 hybridized carbon. Yeah. But it is what it is, and that's a common way of showing the sugar structure. So you just have to follow your way around the ring. 1, 2, 3, 4, and 5, and at each position you draw, the hydrogens are optional, but you draw the OH groups in the correct orientation, up versus down, and so on. That's fine, and in particular, that's the way that if you're going to draw ribose or deoxyribose, like for DNA, that's a very common way of representing the sugar. They're all sort of the same in the sense that they have the stereochemical information. If you know this structure, you can get this one. So I'd prefer us taking an organic chemistry class, me being an organic chemist, I prefer the drawing that gives you an actual sense of what the shape of the molecule looks like. All right. With that, we do need to talk about something else that I also hate, and that is the so-called fissure projection. And I'm doing this only because you're going to encounter it in your future. I refuse to ask you any questions about this on an exam. So it just, and I understand that there's a use for it, but it's frustrating. So the first thing you need to know about a fissure projection of a carbohydrate is that it's not about the cyclic form, it's about the linear form. And the cyclic form is the form that dominates under regular conditions in solution. And so the fissure projection showing you the linear form of glucose is mostly about keeping track of stereochemistry. But you have to know what you're doing in order for it to be useful. I am going to show you how to convert the structure of glucose into, as shown here, into the fissure projection. And I'm going to do it for your benefit and not because I like it. So let's just remind ourselves of what the open chain form of glucose would look like. You should have seen this before as we talked about hemiacetals, right? So the carbon that's bonded to the two oxygens is the hemiacetal carbon. This oxygen is the one that becomes the aldehyde. This one becomes an OH group. You simply erase that bond, put a pi bond there. Behold, the linear form of glucose. All right, open chain form. And actually, since it's now not a six-membered ring, and because carbon 1 is no longer a stereocenter, we can drop the beta and the pyran, and simply this is now just called D-glucose. The name still accounts for stereochemistry at carbons 2, 3, 4, and 5. Now, to get from as I said, the chair conformation of glucose to the fissure projection, not very good at this. We're gonna, again, change this one to an OH group, and this one becomes an aldehyde. The abbreviation for aldehyde is CHO, and so, all right, then you're going to straighten out the carbon chain with 1 on the right and 6 on the left. Shoot, I don't like this. I really, really don't like it, but what are we gonna do? Actually, so that's where we're going, but before we get there, as I said, we want carbon 6 to be on the left. If we straighten things out, as it were, carbon 5 would be on the left and carbon 6 would be pointing upward. So what we're gonna do is rotate around this carbon-carbon bond such that here's carbon 5 and here's carbon 6. All right, so here's 6, here's carbon 5. We just need to decide in which direction after we do that the OH group is going to be. Let's see. Turn. Why is this not working for me? Yeah, it's going to be down axial. So that's, you may have to build a model to be able to see that, but we're rotating around this carbon-carbon bond such that the hydroxymethyl group carbon 6 now occupies the position of this OH group. So basically we're grabbing that OH group and rotating it down into the page. Okay, with that in mind now, we can redraw this Haworth projection, and if we have carbon 6, the CH2OH group, then a hydrogen would be pointing upward and an OH would be pointing downward. If you're frustrated, so am I. I did not make this up. All right, then we're going to unfold or unwrap this chain with carbon 1 here, oops, and carbon 6 here. And carbon 1 is an aldehyde, CHO. Carbon 6 is a hydroxymethyl group, CHOH. Then we're going to draw cross lines for carbons 2, 3, 4, and 5. And then when groups are down, we're going to have them down here in the fissure projection. When groups are up here, they'll be down here. Okay. And then, if you want to make it even worse, we're going to rearrange things so that the CHO is on top, CH2OH is on the bottom, carbon 1, carbon 6. And then you just have to keep track of left and right. And for a long time, this is how you knew that glucose was a D sugar, because the last OH group on carbon 5 was on your right. All right, so that is the Fissure projection of D-glucose. It technically does have a three-dimensional meaning. We're several steps removed from that at this point, right? All that we're really getting from that is just that the stereos, we're seeing here a remnant of what we saw up here with this sort of down, up, down kind of thing along the ring. I don't like that, but I sympathize with it because when people wrote scientific papers in the past with typewriters, they didn't have the ability to draw things like this. And so this was just a really convenient way that just relied on straight lines, which are easy to come by on typewriters, to show the structure of glucose. So that it is what it is. You may encounter it in your future. Knowing what you know now about mannose and galactose, it would be straightforward to take this Fissure projection of D-glucose and convert it into mannose or galactose. You just switch the appropriate stereocenter, right? Okay. And then this is really not useful, but if you desire a way to sort of if you want to understand, this does sort of have a three-dimensional meaning. It's terrible. You're going to hate it, but I'm going to show it to you, and then I'm going to forget it that I ever did so. Technically, you're looking at each of these stereocenters from the following perspective. So here's C2. The OH is coming out towards us, but to the right, the proton is coming out towards us to the left. This aldehyde group is back away from us towards the top, and the next carbon is back away from us towards the bottom. And we can continue that way, sort of all the way down through the Fissure projection. Yeah. 1, 2, 3, 4. All right, so there it is. I don't really know whether you're going to encounter stuff like that. My guess is you'll see things like this in biochemistry. It's possible that on standardized tests, they're going to show you that kind of thing. I just want you to have seen it before, but again, I promise not to ask you any questions about it. Okay, so I've dispensed with that particular obligation. Let's talk about the alpha and beta anomers of glucose. So we'll just draw them again. Here's the beta anomer. And as I've said, this is in equilibrium with an open chain form. Okay. And then that is in equilibrium with the alpha anomer. And you can see to get from the alpha anomer to the beta anomer, you just need to get to the open chain form, and then if you rotate around one of these carbon-carbon bonds, you can change the position of the aldehyde, okay? So in aqueous solution, the alpha and the beta anomers are actually in equilibrium with each other. There's another pathway for this equilibrium. You could draw an oxonium ion that looks like this. This should look somewhat familiar from way back in the days of acetal chemistry. Basically, you would need to protonate the OH group to turn it into a good leaving group, and then it would get kicked off by the oxygen to give you the oxonium ion. And that's another way that you could interchange alpha and beta anomers. If at this point water attacked the oxonium ion from below, you'd get the alpha anomer. If it attacked from above, you'd get the beta anomer. Okay, and I admit I am not showing you the protonation process, just showing you the oxonium ion intermediate. So two different pathways for this same process, converting alpha anomer into beta anomer. This is called mutarotation. I'm not totally sure why, what the muta means, other than this isn't a real rotation. You're breaking bonds, but it looks like you're basically rotating your group from here to here. Those two stereoisomers, the alpha and the beta anomers, are, as I said, in equilibrium. And there's an interesting lesson to be learned here. I think maybe some of you will recall having learned something about axial versus equatorial in 351. Sound vaguely familiar? Which is more stable, having something axial or equatorial? Equatorial because of sterics, right? And we have these things called A values, which basically tell you in terms of free energy how bad it is to have a group axial versus equatorial. These are actually derived from equilibrium constant experiments where they measure the difference in energy between an axial versus equatorial conformation. For the OH group, that number was about 1 kilocalorie per mole. I guess I've already got the units there. So about 1.0. And you can use that number, that's a free energy number for how, it's basically, delta G, for how much more stable it is or how less stable it is to have something axial versus equatorial. A here is for axial. If you use, please do not do this math, if you use the Gen Chem definition of equilibrium constant given a difference in free energy, you can calculate what ratio you expect for beta to alpha based on the A value. And that number here would be about 75% beta and 25% alpha. But actually what we observe is different from that. And so there's something interesting to learn here. We actually observe 67% beta and 33% alpha. So what we see in terms of actual equilibrium is we see more alpha than we can account for based on sterics alone. Okay, so what's going on here? There's a rule of thumb organic chemists tell each other that if it's not sterics, it's got to be electronics, which just means if you can't explain it by groups being large, then you start to have to think about stability and what's going on with electron density in the molecule. So what I've shown you here, this observation that we have more of the alpha anomer than we can account for, this is called the anomeric effect. And if you look up that term, it says it's a contrasteric or against steric bias for the alpha anomer instead of the beta anomer. And how do we explain that? Well, to do this, we need to go back to some molecular orbital stuff. Yay, right? I'm very thrilled about that. So I'm going to draw the alpha anomer. And I want us to think about the anti-bonding orbital that's associated with this bond between carbon 1 and this OH group. That's a sigma star, right? So I want to draw the carbon oxygen sigma star for this carbon 1. There is a node in between the two atoms, and we have small lobes pointing towards that node, and then larger lobes pointing away or opposite the space between the two bonds. The sigma star is projected directly 180 degrees opposite the carbon-oxygen bond, and so you have a large lobe here pointing backwards directly up towards the top of the page. I'm using, as we've done before, color to represent change in wave function sign. This is the anti-bonding orbital if you, right, and it's empty. So this is the empty carbon oxygen sigma star. On an adjacent atom, you have, on this adjacent oxygen, you have non-bonding lone pair electrons, okay? And it's fine for our purposes if you think of those non-bonding lone pair electrons as being in an sp2 type orbital, or an sp3 rather type orbital. It doesn't have to be that way. In fact, there's some data suggesting that it's not that way, but that's going to be fine for our purposes. Here is a filled non-bonding lone pair on oxygen. Now, energy-wise, non-bonding lone pairs are higher in energy than orbitals that are in bonding orbitals, because the whole point about bonding is to lower the energy of electrons. You're not involved in a bond, you're fairly high in energy. Anti-bonding orbitals are empty and are higher in energy than non-bonding orbitals. What I'm going to talk about now is a concept that you would have learned a little bit in 351, possibly. Some of my colleagues talk about it, others don't. Hyperconjugation is overlap of a filled orbital, a high energy filled orbital with a relatively low energy empty orbital on an adjacent atom in the same molecule. It's similar to conjugation. Remember, conjugation involves side-by-side overlap of p orbitals to create resonance. Hyperconjugation also involves side-by-side overlap of orbitals, but they don't necessarily have to be p orbitals. In this case, it's an empty sigma star and a filled oxygen orbital. And this has a couple of consequences of hyperconjugation. First, the lone pairs on the oxygen spread out. They actually spread out towards carbon 1. And remember that electron delocalization is stabilizing. A couple other consequences. You might imagine if I partially delocalize electron density into the sigma star, that bond between carbon and oxygen gets a little bit longer. And that's true. And both of those things work towards this observation of having more alpha anomer than expected. If having the carbon-oxygen bond a little bit longer means sterics is a little bit less of a problem. All right, there's more to say because we need to compare this situation with what's going on in the beta anomer. But for now, what questions do you have about hyperconjugation? Yeah,
Why does that carbon oxygen bond get longer?
say that a little bit louder.
Why does the carbon oxygen bond get longer?
Why does the carbon-oxygen bond get longer? In part because you're donating electron density into an antibonding orbital. Not completely, it's just a little bit. If you fill the antibonding orbital completely, then the bond breaks. In this case, you're only doing a little bit, so the bond gets a little bit longer.
Okay, so it's one going down.
Yeah, yep. This is the bond that gets longer. Yep. Okay, what else? I guess another way of looking at that is if we were back in the days of carbonyl chemistry, if we turned that into a good leaving group, donating those electrons completely into that antibonding orbital is what kicks off the leaving group. So doing it a little bit makes the leaving group leave a little bit. All right, what else? Okay. If we look at the beta anomer, you'll see that the orbitals don't line up as well. So when the OH group for the beta anomer is pointing up in this equatorial position, now look at where the sigma star is relative to the lone pair on that oxygen. Notice that most of that sigma star is pointing backwards, sort of under the ring. It no longer lines up with this lone pair, and it also doesn't really line up with that lone pair either. This lone pair that's sort of in an equatorial position is lined up with the node in between the two nuclei. For hyperconjugation to work, you need the lone pair to line up with the large lobe on the sigma star in parallel, side to side. And over here, the orientation between the non-bonding lone pair and the carbon-oxygen sigma star is almost perpendicular. Orbitals that are perpendicular to each other don't interact. Kind of like it's got to involve the cross product or the dot product or something like that. But in any case, orbitals that are perpendicular don't interact well, and so there's much less hyperconjugation for the beta anomer than there is for the alpha anomer. Yeah?
Would electro-repulsion play any role as well, or not really?
Electron repulsion?
Yeah, well, because both options would be more electron-rich.
That's interesting. I hadn't thought about that. I guess you would predict there would be some, you would need to know sort of the partial charge on each of these atoms to be able to tell how bad it is, how bad that is. I think distance-wise, I think this distance here between the two oxygens is about the same as it is here, except for the fact that this bond is a little bit longer. All right, there's more we could say about that, and the anomeric effect is sort of a favorite topic of organic chemists, but I think you know enough to be getting on with. What I want to do now is talk about glycosides, which are sugar acetals. And this will give us a chance to talk about carbohydrates that are longer than just one sugar. So, a simple glycoside you can make by taking I don't like that. I don't like the chair. You can take a simple glycoside, or make a simple glycoside by Sometimes when people want to communicate, I have a mixture of alpha and beta anomers, because that's what you get when you put glucose in solution. You get a mixture of alpha and beta anomers. You use a squiggly line here, sort of between the equatorial and axial positions. That's not meant to communicate anything three-dimensional. What that is meant to communicate, I have a mixture of alpha and beta anomers. You can purify one anomer from the other, though if you're just going to turn around and put glucose in water, it's just going to form the mixture of alpha and beta anomers again, so that's somewhat counterproductive. All right, so if you want to make an acetal from this hemiacetal, you would just need some alcohol and some catalytic acid. What we would have used based on our earlier chapters would have been like para-toluene sulfonic acid as an example. And what happens there is you swap out the OH group of the hemiacetal for the alcohol. All right. This mechanism is a review mechanism. You should be able to draw this, and for simplicity's sake, what I will do is draw it like this. We protonate the OH group. And there were a few questions, at least on a previous exam, about mechanisms like this that were things that some students struggle with. So if looking at this now is a bit of a, if it's not looking familiar and there's still issues you think you have with the mechanism, it would be a good idea to go back and review this. All right, so we turn OH into a good leaving group. It leaves, we get the oxonium ion, and then our alcohol attacks that oxonium ion. We get a tetrahedral type intermediate. The thing that drives this reaction to completion is the fact that we are removing water. And then we restore our acid catalyst, and that gives us that product. Okay? So I didn't notice how much I abbreviated because I didn't want to draw all of this stuff again and again. In my experience, it takes students a while to be able to jump easily back and forth between this and this. If that's a challenge for you, you should work on that because that'll make your life a lot easier when drawing mechanisms if you know how to abbreviate. All right, so that is a simple glycoside. This is the methyl glycoside of glucose. But one of the things I think we mentioned previously is that glucose itself is a polyalcohol. You've got a lot of OH groups that are available to you, and you could, instead of using methanol, just as easily have used an alcohol from another molecule of glucose to create a linkage between that other glucose molecule and this one through this sort of acetal carbon. So let me show you what one of those would look like. Here's one chain of glucose. Instead of having an OH group here, I'm going to have this oxygen be from an OH group on another sugar. Okay? So do you see how this whole sugar now occupies the position of that methanol? This is the acetal carbon, that's the acetal carbon. All right? What I've drawn for you here is a 2-carbon carbohydrate. It's actually called cellobiose. It's you get it from cellulose. But what we want to talk about is what's called the glycosidic linkage between the two sugars. Remember I told you glycoside meant a carbohydrate acetal. The glycosidic linkage is the acetal linkage between two sugars. The acetal carbon is C1, carbon 1 of the sugar on the left. The alcohol from the second sugar, the one on the right, is from carbon 4. And then the stereochemistry of that acetal carbon here is beta. That is, the OH group is up. And so we will call this glycosidic linkage a beta 1,4 linkage. And that's how people talk about it. Beta tells you the stereochemistry of the acetal carbon. The 1 tells you you're linking carbon 1 on one sugar and carbon 4 on the other sugar. And yes, you would technically, if you wanted to name this whole molecule, you would technically need a way to talk about that this is glucose and this is also glucose. We won't worry about that, but what I do want you to be able to, or do want you to do, the skill you need to have is the ability to look at a structure and then tell me what kind of glycosidic linkage that is. That's a beta 1,4 linkage. So, yeah, go ahead.
Is there a reason why it's not carbon 4?
Right, is there a reason why it's carbon 4? It could have been any of them. Yeah, if you were making rock candy on your stove, you would make glycosidic linkages involving any of these, and you'd get a very large branched carbohydrate, which is why that if you do this, which is why if you cook it for long enough, yeah, you get something that's really sticky and then solidifies. This is done enzymatically in biology. So biology doesn't need protecting groups, it just controls which one does the chemistry.
So it's not a matter of like carbon 4 being favored that.
No, it's not a matter of carbon 4 being really favored, it's just that the enzyme has made it that way. Yeah.
So I know with biochemistry, with liver, glycogen, you have to know like 1,6, 1,4, all that stuff.
Right.
For this class, you want us to recognize any of these linkages and you have the cellobiose.
Given what I've told you now, if you can count and you know what beta is, you should be able to talk about any linkage. Yeah, if you know what alpha versus beta is, and then if you can count, you can figure out what kind of linkage it is. Yeah.
Did you say that oxygen from the alcohol group that's linking, is that from carbon 4 or carbon 1?
This is from carbon 4. So the bond that we make, that's sort of how you divide the thing up into two sugars. This oxygen belongs to or came from the OH group on carbon 4. Yeah.
So the reaction to make that glycosidic is that you lose an H2O.
Yep. Yeah, the reaction to make a glycosidic linkage, do you lose H2O? Yeah. Okay. Others? Yeah.
Is that always under like acidic conditions?
Is it always under acidic conditions? Actually, you don't. I mean, you need a little bit of hydronium to make this happen, but you don't need a lot, and you can tell this is the case because a rock candy recipe is basically corn syrup and water and then like food coloring at the end if you want to, maybe a little bit of vanilla and flavoring. I don't think you even add any acid, so there's apparently enough hydronium even at pH 7 to make this happen with heat, and you use heat to overcome the activation energy. Steam comes off, that's not only water boiling, but that's also water being released from the dehydration reaction. course, biology will do this differently. We won't talk about the biosynthesis of glycosides, but basically it is what you would expect. You need some way to turn this into a good leaving group, and nature has a way to do that. All right. Let's look at some other carbohydrates, and we'll just say what the linkages are. Let's see. So I'll draw the two carbohydrate or the 2 sugar carbohydrate maltose. This is if you take 2 glucose molecules and you link them together a little bit differently. Oops. Where's my pencil? All right. What kind of glycosidic linkage is there? Alpha what? What are the numbers then? Alpha 1, 4. First, identify the acetal carbon. Then, depending on the sugar, you'll put the number of that acetal carbon, which in this case is 1. And then you find the OH group on the other sugar and figure out what carbon it was attached to. That's carbon 4. That's alpha 1,4 linkage. All right. Just as well do table sugar, which is sucrose. I hesitate to do this example, but let's just forge ahead. All right. On the left is a carbohydrate you've seen before. On the right is one you haven't. So, what's the carbohydrate over here on the left? That's glucose, and the acetal carbon is here, and the orientation is alpha, right? So what kind of glycosidic linkage would you call this? Alpha 1, 2 is probably, yeah. The reason I'm hedging and saying probably, I don't really like how I drew one of those carbons. The reason I'm hedging and saying probably is because sucrose is different. Notice that the oxygen on maltose came from a hydroxy group on carbon 4. Just a regular boring hydroxy group. Notice that for sucrose on carbon 2, that's also an acetal carbon. So this is unique. In sucrose, unlike any of the sugars we've looked at before, in sucrose, the 2 acetal carbons are actually linked to each other. Whereas in maltose, the acetal carbon was linked to just a regular OH group. The other acetal carbon was there. This allows us to illustrate something that you'll hear people talk about when it comes to carbohydrates. They will call things like glucose or maltose a reducing sugar, whereas sucrose is a non-reducing sugar. You heard of that before-ish, vaguely, maybe? Okay, yeah, go ahead.
Just a refresher, what makes the acetal
What makes the acetal carbon acetal? Two oxygens bonded to it, and they're both OR groups, not OH groups. If one was an OH, it'd be hemiacetal. If both were OHs, it'd be a hydrate. All right. The reason that maltose is called a reducing sugar is because it has a free hemiacetal that can have an open chain aldehyde form. And you can actually do chemistry with that. You can reduce things with the aldehyde. There's a demonstration I should have booked for today where you can use a carbohydrate to actually reduce a silver salt, silver plus, to metallic silver. You can make mirrors this way. But sucrose doesn't do it because sucrose doesn't have a free hemiacetal/aldehyde. Okay. Couple other carbohydrates we should talk about. And then I think we can be done. You've heard of lactose. Lactose is the beta 1,4 linked linkage between galactose and glucose. So we draw it this way. On the left, we're going to draw galactose. That's the C4 epimer of glucose. It's a beta 1,4 linkage. So here's one. Here's the oxygen in the beta position. And then that oxygen belongs to carbon 4 of the next sugar. There's the hemiacetal carbon, that's the beta 1,4 linkage. And this is a component of a carbohydrate that's found in milk. And in human infants, they express an enzyme, their intestines express an enzyme that can hydrolyze that linkage. It's called galactosidase, beta galactosidase. As we get older and don't rely on milk for nutrition as much, expression of that enzyme decreases. And so if you don't have enough of that enzyme, you're not necessarily able to hydrolyze that linkage, but bacteria can, and gut bacteria will do so and sort of go a little bit crazy. And that leads to the sort of gastrointestinal symptoms that are associated with lactose intolerance. Interesting bit of human history and evolution. As cattle became domesticated and people that lived in colder areas learned to gain nutrition by storing dairy products as cheese and butter and so on, there was a selective advantage if you could actually up your expression of beta galactosidase and not get sick upon eating milk and cheese and so on. And so that sort of innovation and mutation happened in Europe thousands upon thousands of years ago. And so if you have ancestors from Europe, you are likely not lactose intolerant. If you don't, you might be. And that's just has to do with, as I said, human evolution and domestication of animals and eating cheese during cold European winters. All right. There's more I think we could say, but I would just be drawing structures that are already drawn for you in the textbook. What I want you to be able to do is identify carbohydrates. I want you to be able to identify glycosidic linkages. You should know glucose from galactose from mannose. I guess one last thing on our survey that I want you to be able to recognize is just because it'll show up in carbohydrates that you see is something called glucosamine. This is replacement of the C2 hydroxy group with an amino group. And you don't need to know how this happens chemically or enzymatically, but you are going to see this carbohydrate in a number of different settings. In particular, if you put an acetyl group on that nitrogen, you have something that's called N-acetylglucosamine. And this is an important carbohydrate in glycoproteins in biology. So N-acetylglucosamine. There's nothing really to memorize here. If you see a nitrogen there, you can still define glycosidic linkages in exactly the same way. If you string together multiple N-acetylglucosamine subunits via beta-1,4 linkages, you have chitin, which is insect exoskeleton. All right, so questions about what you need to know? All right, let's take a break. When we come back, we're going to do lipids, and you've got some carbocation rearrangements in your future.